Okay, so then I will talk about, analyzing methods of analyzing relaxation data. And so just to start, of course, you've seen a couple slides that look kind of like this from Fabian, but I'll just briefly summarize. We're all familiar with relaxation. We know that when we pulse magnetization from the z-axis down to the xy plane, it'll oscillate, but it'll also decay in the xy plane due to T2 relaxation, and it'll recover to the z-axis due to T1 relaxation. And that behavior, of course, is due to motion in the system. Different copies of each spin in the system experience slightly different environment due to the random motion, and so that leads to dephasing. And so just to show you that once what that kind of looks like, I've got here a simulation, an MD simulation of a lipid bilayer. Just show you one half of the bilayer. And what I've done is on each carbonyl, or on a carbonyl in each molecule, I've shown you the CSA tensor. And that CSA tensor is going to move around with the carbonyl, with the CO bond. And that is going to result in variation in the trajectory the magnetization is going to take. So each blue arrow is the magnetization for a given carbon spin. And so this will oscillate around an external magnetic field, and that will be the same for every spin. But for the different copies of the lipid, it will be slightly different evolution because of the modulation of the CSA interaction. So that looks like this. Of course, as you start out, all the spins are doing roughly the same thing. But the total magnetization you see starts to decay, and that's because the spins start to get out of phase. And additionally, the magnetization starts to recover to the z-axis. And so each spin is behaving somewhat randomly, but it results in a very predictable net behavior of the relaxation, the T1 and the T2 here. And so the question is, well, can we use that relaxation, and how should we use that relaxation to characterize the motion leading to it? And so just as a disclaimer, the timescales in this movie are hugely unrealistic, so don't take it too seriously. Anyway, so what we have is relaxation, and relaxation in the simplest case is a function of the order parameter, and I'll usually relate 1 minus s squared to the amplitude of motion. I'll say a little bit more on that on the next slide, and the correlation time. So if the motion in my system were well described by a single correlation time, then my relaxation rate constants would depend on order parameter and correlation time like this. And so just for examples, I show you R1, R2, and the NOE. And what you see is as 1 minus s squared, 1 minus the order parameter squared, increases, then the rate of relaxation increases. That is, the time constants of relaxation themselves get shorter. That happens for all the rate constants. And then for the R1 and for the NOE, if my correlation time matches the sensitivity of the experiment well, I get very fast relaxation. And for the T2, of course, as the correlation time gets longer, the rate constant gets faster and faster. So how can I use this to get some information on dynamics? Sorry, I'm skipping a slide. I have also the order parameter. I just have one slide on this, but I think it's important to understand. If I know what my motion looks like, say I can say that a given bond, its motion is basically wobbling around in a cone, so it isotropically samples everything within this cone. Then as the amplitude of motion is, as the cone gets bigger, 1 minus s squared gets bigger. Now the problem is, though, I don't really know that that is the way my orientations are sampled. My orientation sampling could happen a lot of different ways, and so just to show you some examples here, these are just simple models. It needs not be one of these simple models, but wobbling on a cone, wobbling in a cone. I have a symmetric two-site hop, so these sites are equally populated. And here these two sites are not equally populated, and then a multi-site exchange. And what's interesting here is all of these orientation sampled have the same order parameter. So you really can't get the exact orientation sampled from the order parameter. But what we're going to do is focus on actually correlation times in this talk. Okay, so suppose that my relaxation depends only on a single internal correlation time and an order parameter. Well, if I were to measure one rate constant, I would get a dependence that looks like this. And so in this case, I say, well, what if I measure R1 of 0.5, so a T1 of 2 seconds? Well, that relaxation rate could be explained by anything on this contour level here. So I could have a large amplitude motion where the correlation time is far away from where my experiment is most sensitive, or I could have a relatively small amplitude motion, but the correlation time is well matched to where my rate constant is most sensitive. But beyond that, I can't deconvolute these two parameters. But if I have a second measurement, then each measurement provides me with a contour. And I can put those two contours in a single plot, and where they intersect is my correlation time and my order parameter, my amplitude. So the question is, well, how realistic is this to have one correlation time, or really even just a few correlation times? So we can get our dynamics for one correlation time using just a few rate constants. In this simple example, just 2 rate constants. If we have overall tumbling in the molecule and an internal motion, we can use the simple model-free approach. If we have 3 correlation times, we can use the extended model-free approach. But the question is, how realistic is this, that we actually have so few correlation times? And so I wanted to just compare, well, here's motions with 1 correlation time. If you have isotropic tumbling in solution, so basically a spherical molecule, and the internal motion is very small or non-existent, then you have 1 correlation time. If the only motion you have is 2-site hopping, so you just sample 2 orientations, well, then you get 1 correlation time. And if you have symmetric 3-site hopping, basically like the hop of a methyl group, you would get 1 correlation time. And so I don't want to promise that these are the only 3 examples, but these are what I could come up with. In contrast to that, this is a list of motions that have multiple correlation times. And so the first is, of course, if I have anisotropic tumbling in solution, if that tumbling is axial symmetric, I already have 3 correlation times. If it's asymmetric, I have 5 correlation times. I could have multi-site exchange. So if instead of hopping between 2 sites, I hop between several sites. Here in the 6-site hop model, I calculated it out and determined that there's actually 3 correlation times active. You might have restricted diffusion. So those are the wobbling in a cone, wobbling on a cone type motions, and these also generate a series of correlation times. Perhaps often overlooked and fairly common is if you have a protein with any long-range structure, you get actually modes of motion. And the way to understand this is, well, so here I have HET-s fibrils, and what we had done is looked at motion on different time scales. And we correlated that motion with neighboring motions. And we found a very short correlate time scales. Well, it was uncorrelated at intermediate time scales. The length scale correlation increases, and that continues happening for longer correlation times. The length scale keeps increasing. And it's nothing special about these 3 correlation times shown. Every length scale in between potentially also leads to a motion and a different correlation time. And so if you've got this kind of behavior, what you'll actually have is a practical continuum of correlation times. And so here we saw this in the fibrils. That's based on an MD simulation, although it was cross-validated with the experiment. But other MD simulations, if you look at a helix, you see similar behavior. And so this kind of thing is going to lead to almost a continuum of correlation times. And this idea isn't unknown at all. It's actually a fairly familiar idea. You just have to go to some other fields. If you look at polymer dynamics, and if you look at lipid dynamics, they have what they refer to as power law behavior. And this is where the rate constants, as you vary magnetic fields at the Larmor frequency. These end up being proportional to the Larmor frequency raised to some power, and that power depends actually on the dimensionality of the correlation. So if you're correlating across, if you have increased correlation across one dimension, you have D1. If you have it across 3 dimensions, you have D of 3. And so in these cases, when you have power law behavior, what we're saying is actually that you have a continuum of correlation times resulting from motions that have a varying correlation length. The next example where we get multiple correlation times is, of course, if multiple motions affect the relaxation. So here we look at an isoleucine, and this is a little bit inspired by some of the things that Fabian does just from conversation. But anyway, we look at, we say that the motion of an HC bond here, which is leading predominantly to the relaxation of this carbon, is the result of rotation around this bond. It's also rotation around the chi2 bond, also rotation around the chi1 bond, and also motion of the C alpha C beta bond. And each of those the rotations actually can be broken up into 120-degree hops, and also kind of a librational motion in between those hops. And so these 7 correlation functions here, if you take their product, you get approximately the correlation function for the total motion. And you can see that each one of these has a different kind of rate of decay, and therefore a different correlation time. So the librations are all very fast. Basically, the decay after 1 time step in an MD trajectory, so 5 picoseconds. But the methyl hopping is slower. The chi2 hops are yet slower. You have to check the x-axis. The chi1 hops are even slightly slower than that, and also the C alpha C beta motion is a different rate. And the final thing to consider is, well, why might I have multiple correlation times? Is I may have some process like the methyl rotation here, and some slow motion can reconfigure the system, and it changes the rate of the fast motion. So that will also manifest as multiple correlation times. So one of the most important things I want to impress on you here is that there's always going to be many correlation times affecting the relaxation of the nucleus. And the exceptions to this are going to be if there is one motion with a very narrow number of correlation times that is a very dominant motion. But for the most part, you should consider that when you're analyzing your data, that you've got lots of correlation times present. And so the question is, how can you get, how do the parameters you get out of your analysis behave in response to a distribution of correlation times? And how can you interpret those? And so that's what we try to do with what we call the detector analysis. And so we start out by saying, okay, so I have a correlation function. And rather than assuming it has a particular number of correlation times, I just say, well, this has a sum with an arbitrary number of terms of correlation times. And so the amplitudes here sum up to 1, and then the total amplitude of decay is given by 1 minus s squared. And as I mentioned, you have potentially a continuum of correlation times, especially if you have this sort of mode type behavior. And so often we replace the sum with an integral. It means the same thing, we're just summing up multiple correlation times, but now this is a continuous distribution. And here I've replaced the correlation time with the log of the correlation time, so z. So we're going to do this on a logarithmic scale. This is just for convenience, so it doesn't really change anything. And so the spectral density is basically the same integral, but for each exponential term here, now I get a Lorentzian term here. And if you assume this, then you can say that the rate constant for any experiment you measure is just the integral over that distribution multiplied by the sensitivity for the given correlation time. So we just say, well, what are all the correlation times in my distribution? And for each correlation time, I calculate out how fast the relaxation is, and I add that to the total, and I get my total relaxation rate. So these are just examples of R1 sensitivities, so 15N R1, and these are measured at not measured, but calculated at 850 and 500 and 400 megahertz. And if you take it like this, you can kind of think of a relaxation rate constant that you've measured as kind of a window into the motion at a given range of correlation time. So at 850 megahertz, this green line is my window into my motion. And so just to give you an idea. There it is. This is R1 at 850 megahertz, measured for HET-s fibrils, and it's measured on the nitrogen. And so you can see basically how the amplitude, and this is going to be roughly around 1 nanosecond, although it's going to span the whole breadth of this window. So how that varies throughout the HET-s fibrillar structure. Okay, so already when we take this point of view that we have a rather continuous distribution of correlation times and our rate constants are windows, we already have kind of a new way of looking at this, but what we'd like to do is use multiple rate constants and get something more useful. And so you can see the problem here is if I've measured R1 at several fields, all my windows are really relatively similar. So what I'd like to do is get different windows, separated windows. And so these rate constants can be combined to yield one window sensitive to more fast motions and one window sensitive to slower motions. And so what I've got here is I've got my formula for my relaxation rate constant. And what I claim I can do is I can just add up relaxation rate constants at different fields. So zeta here would be different fields. So the 400 and the 500 and the 850. And I could also put in different types of relaxation rate constants here. But I just add them up with some coefficient. And plugging in the formula here for the rate constant, I get this. I swap the integral and the sum, and I get a formula that looks like this. I end up summing up the sensitivities. I can define that as some function. And now I get this thing called the detector response. And the detector response now has one of these windows. And so the trick is just to pick the amplitudes correctly. By the way, you can do this also in solution state NMR, and you can do this in such a way that you remove the overall tumbling. And this is work we did with Fabian. But what we do is say, well, if we've got a molecule tumbling in solution and I know how fast it's tumbling, I can calculate the relaxation if the molecule is rigid, if there's no internal motion. So I take that number and I say my measured rate is that number plus an adjustment. And that adjustment comes from two factors. First of all, internal motion attenuates the size of the interactions. And so I decrease the relaxation due to tumbling from that attenuation. And internal motion induces relaxation itself. So I increase the contribution from the internal motion here. And I add these things together. I get a sensitivity. And with this sensitivity, I can also design detectors for solution state data, and I can remove the tumbling, and I can just analyze the internal motion. So how does this all look? How does this actually practically come together? So what I do is work an example for you here. I assume a distribution of motion. Now, experimentally, I wouldn't really know this. This is the thing I'm trying to characterize. But in this example, I take a methyl rotation and I give it a correlation time and I give it some breadth. And then I say there's also some dynamics due to the motion of the carbon-carbon bond. So I also give this a center and a width. Now, the measured rate constants will be the overlap of the sensitivities of the experiments with this function, and also the motion due to tumbling of the internally rigid molecule. And so that's what this shows you. The top of the bar is the total relaxation rate constant. The black line is the contribution from the tumbling, and the solid part is the contribution from the internal motion. And so what you do with this is you take the contribution from the internal motion, and you take the sensitivities. And so what I do is I've got my sensitivities here, and I take, first of all, the sensitivity of the R2, and so this is data at 400 and 950 megahertz. This is an example for 400, 500, 950. There's no real data here. And I first multiply that number by 0.15. And these have been optimized. I'm not going to get into details of how these have been optimized. I take the next R2 and I add it on with a coefficient of minus 0.15. And I get the sum here in gray. And then I add the R1 at 400 with a coefficient of minus 0.22. I get this function. And I add the next R1 on, and I get this function, and so on, till I finally get a nice detector window. This is a detector window optimized to be sensitive just to short correlation And so I separate out short correlation times as much as I can from all the other contributions to the relaxation. And the way I get my detector response is I apply exactly the same linear combination to the corresponding experimental data. I get a detector response. And so I can do this procedure. I optimize 4 different detectors with the same procedure, but with different coefficients for each detector. And I get a detector analysis. And so these are the results of adding together the relaxation rate constants with the corresponding coefficients. But it turns out that this bar, for example, is equal to the integral of the blue area, the shaded blue area here. And that area is in fact the product of the distribution of correlation times and the sensitivity of that detector. So basically I get a window into the fast motions with this detector. And you can say the same thing for each one of these detectors. And so the blue detector is showing me the very fast motion. And of course it overlaps heavily with the distribution. The orange detector less so, and so we get a smaller detector response. The green detector is capturing the CC motion that you see here, and the red detector also captures it a little bit on the edge. And so without assuming anything about the model of the motion, I can still get these quantitative detector responses. And so you could think of this as kind of a modern model-free approach. And just an example, this is an analysis of HET-s detector responses, and you kind of see how it works. This is primarily very fast motion here, and it's very uniform. In the nanosecond range, I get these detectors, and I see that I get increased amplitudes of motion at turns and near the flexible loop and near the termini. And actually, it's similar behavior in the microsecond scale, although the amplitudes are much lower. Okay, so the question though is okay, we've got these detector responses. Okay, so I should just mention there are a number of related approaches. Spectral density mapping is mathematically it's an instance of the detector analysis where we don't remove tumbling. Lamass's approach is also a special case of, can be thought of as a special case of detector analysis where we do remove tumbling. And impact is closely related, although I wouldn't quite say it's a special case. And in fact, simple model free, if you have very fast motion, behaves also in a similar manner as kind of the detector analysis and in solution. Okay, but the question is, I've got these detector responses, but how can I get a better interpretation of the detector responses? Well, a cool feature of these is when we've got our experimental sensitivities, we add them together with coefficients to get detector sensitivities, nice separated motions. It turns out that if you've got a correlation function that you've calculated from an MD trajectory, you can also define sensitivities for every time point in that correlation function. And you can also optimize detectors in exactly the same way. I mean, it's really exactly the same thing. We use the same software, we just dump in a different set of sensitivities. And you can optimize these to match the NMR sensitivities. And so here you see we do pretty well matching for fast motion, things in the picosecond and nanosecond range. And of course, this is sort of a problem, but kind of an advantage is you see you don't manage to use the microsecond MD trajectory to match the microsecond motions, which tells you that you can't analyze, you can't compare microsecond motion obtained from NMR to MD dynamics based on a 1 microsecond MD trajectory. So you also kind of get an idea of how good your comparison is going to be when you try to optimize these detectors. So I just want to show you, hopefully very briefly, just how we use this MD and this NMR together. And so in this case, we took the HET-s picosecond and nanosecond dynamics and compared it to an MD trajectory. And so these are detector responses. The colored is the experimental data, and the black line is the simulated data. And you can see, for the most part, we're in very good agreement. And then we took this a step further. We analyzed the MD trajectory for correlation for the particular correlation times. And so this is where we get out this information that the correlation time is a result of variation in correlation length in the fibril. So that's that mode motion that I talked about before. We also looked at POPC membranes, and again, colored is experiment, black is simulation, and for the nanosecond motions, we get very good agreement once again, but for the microsecond motions, of course, we don't compare because the trajectory is just not long enough. And if you say, well, what does my detector response mean? Well, one thing we can do is we can take the MD trajectory. Now, if I can manage, I'll start that over so you can see it from the beginning, but I color code the detector and the amplitude of the detector onto the molecule as it traverses different time scales. And so that's what you see here, is you can kind of get a picture of what is the detector response actually relating in terms of actual motion. And so we do this in one further step. Is in the lipids, what we did is we separated the motions explicitly with the MD trajectory, and we analyzed them with detector analysis. And this is the result. To keep it brief, I won't go into great detail on this. But we said, well, the motions have been separated, so it should be reasonable to describe those motions with a few parameters. And so each motion, we and for each residue, we described it with an amplitude, a width, so a distribution of correlation times with a width, and with a center of that distribution. And so we from those distributions, we could again calculate detector responses and compare it to the experiment. And we did a small refinement on the correlation time of internal motions. So one parameter for every residue, for every measured experimental resonance, actually. We adjust one parameter to refine the results to match the experiment better. And then we get a picture of the distribution of correlation times as a function of position in the molecule for each one of those individual motions. We can combine all these individual motions to get the total motion, so we get the total distribution. And so if you say, what does your detector response mean? Well, it's the integral of these sensitivities with this distribution. And so what I did is highlighted on here, the coloring tells you, well, which detector is picking up which part of the distribution. And so just to wrap up, so I'm all done, is just remember motion is inherently multi-exponential. And so how are your parameters going to behave? So I present you the detector analysis, and I just want to mention that all these related approaches, mainly the difference between these and detector analysis is generally applicable, whereas these kind of need to be applied to specific cases and specific data sets. And so just, I've been working on this since my time at ETH, but now of course we're continuing to work at in Leipzig, where we're in particular working on the lipid analysis. And so I'd like to just thank all these people.